Let's start with the device configuration. I have already prepared a project with an ET200SP CPU and I/O modules for this. For an EMC compliant setup, we recommend a blank base unit between electronic modules and the e-starter. For this, we project an BU cover with a width of 15 mm, but a potential distribution module would be also an alternative. Also make sure to select the correct base unit and adjust it if necessary. Next, we select the e-starter that match our hardware setup and place them next to the BU cover. Optionally, the 4DI basic submodule with 4 digital inputs can be added. Actions such as a manual control can be parameterized for these inputs. More on that later. For the cyclic process image, a selection of measured values can be easily added by choosing a PI extension. Currently, this function is only available for decentralized configuration with an ET200SP interface module. Now, only the cover for the right blank base unit is missing. I have reserved this for the later expansion with an additional e-starter. Let's now look at the parameterizable properties of the e-starter. Starting with the I/O addresses. Here, not only the standard parameters for the address space can be configured, but there's also a very helpful button for automatically generating PLC variables for the e-starter. This saves a lot of time and effort for reading documentation and manually creating the PLC variables. In the basic parameters section, we find the most important parameters for operation, such as setting the rated current for overload protection, selecting the load type, and the interval of a maintenance timer. The new Smart Start function can also be activated here. This significantly reduces inrush currents and mechanical stress during startup. Try it in your application. Additionally, for reversing applications, you can choose between lifetime or switching time optimized switching. In the protection function section, warning and shutdown thresholds, as well as the behavior for protection functions such as overload, asymmetry, ground fault, and blockage can be activated and set. Furthermore, our e-starter offers the possibility of upper and lower current limit monitoring for condition monitoring. So deviations from normal operation are immediately detected and reported. Immediate shutdown of the consumer can also be carried out. Here we set an upper fault threshold of 150% and a pre-warning threshold for maintenance at 110%, depending on our application. The reference value for this is a parameterized rated current. The 4 inputs of the 4DI submodule are already preset for a local control station and can be adjusted in their action and behavior if necessary. Under the Fieldbus interface, there are settings for activating and deactivating process alarms, such as group fault and group warning. The behavior in case of communication failure or PLC stop can also be adjusted to our requirements here. For applications where the direction of rotation plays an important role, monitoring of the permissible main power rotation can also be parameterized to prevent accidental starting with the wrong direction of rotation. After making all the settings, we can now compile the project and download it into the controller, to then perform an initial test. I will not go into the programming of the controller in detail, as this can be handled very individually. After the project has been loaded and the controller has started without errors, the run LEDs on the controller and modules light up green continuously. Let's now take a closer look at the cyclic process image of the eStarter. For this, we create a watch table and add the automatically generated PLC variables for manual monitoring and control. Alternatively, an I/O check can also be carried out by using Pronata tool. By controlling the motor CW tag for clockwise to 1, the motor can be started in the right direction and we immediately receive feedback via the input signals such as motor on. Online and Diagnostics offers us views for measured values, statistical data, current device parameterization, and diagnostic information through TIA integration. In the device status view, we can easily display the current status of the eStarter. With the attached motor brake, I now simulate an excessive load to the motor, which is shown to me as a group warning and a plain text message. In the event of a short circuit on the load side, which I switch on here on the model via toggle switch between phase L1 and L2, the eStarter immediately shuts down. This signals the fault with the red blinking load LED and provides detailed information in the diagnostic view. In the eStarter's logbook, all occurred faults, warnings, messages, such as switching operations, can be traced with timestamp. After the short circuit has been eliminated and the fault has been acknowledged, the motor can be switched on again immediately. By setting the motor CW variable to 0, the motor is switched off via the eStarter.